So here we go. We're on to the context and applications questions, the long questions in paper 2. There are 4 of them there to do. It's going to be your best 3 that count. This question here is a stats question. You can kind of say it's kind of linked to probability as well because the Z-score question's in there. Let's have a look at it. It says the speeds of cars traveling on a section of motorway have been found to be normally distributed with a mean of 95 kilometers per hour and a standard deviation of 3 kilometers per hour. Calculate the percentage of cars to have a speed between 89 kilometers per hour, which is below the average, and 98 kilometers per hour, which would be above the average. So, with that, you might want to just read it a couple of times, get your head around it. But really what we're saying is, what's the probability that, a car selected at random would have a speed between 89 kilometers per hour and 98 kilometers per hour? We know, of course, we can't calculate that straight away. We know how this works at this stage. We're going to have to get the Z-score. So we're going to use our standardizing formula. If I said to you, what page is this on in the table book? I hope you're saying page 34, the standardizing formula. So you're going to get your Z-score using the formula Z is equal to X minus mu over sigma, where X is your score. Like, so, 89 can be your X or 98 can be your X, depending on, when you're dealing with each particular one. But mu is your average, of all cars, and sigma is your standard deviation. So we'd start off. And so again, what I'm doing here now at this point is I'm using my formula here. I'm saying, well, I'm finding the probability of having a score, which in this case, the speed is between 89 and 98. But I'm going to, instead of having X, I'm going to get Z. And basically how I'm going to calculate it is I'm going to say, well, 89 minus 95 over 3, that's going to correspond to my 89, and corresponding to my 98 would be a Z-score of 98 minus 95 over 3. When I do my calculations, that's basically saying the 89 kilometers per hour is 2 standard deviations below the mean, so minus 2, and 98 kilometers per hour is 1 standard deviation above the mean. And of course, that makes total sense. Why is that? Well, if I draw my standard normal distribution curve, so we can see there that's our norm, that's our bell curve, right? And it's standard normal with a mean of 0, standard deviation of 1. And in our case, in the case of the actual question, it had a mean of 95 and it had a standard deviation of 3. So sigma was 3. So in our case, right, 1 standard deviation above the mean brings you to 98. 1 standard deviation below will bring you to 92. If I go another standard deviation above, I'm up to 101. Another standard deviation below, down to 89. Another one above brings you to 104. Another one below brings you to 86. So it's clear looking at that, like what we're looking for is the probability that a Z-score, I overcooked it there, that any car would be between 1 standard deviation above the mean and 2 standard deviations below the mean. Now, some of you, no doubt, are thinking to yourself, oh, I wonder, could I use the empirical rule to calculate this? And you could, and maybe it'd be no harm to do it for yourself to see how accurate it is, but it is more accurate to use page 36 and 37 to get your Z scores and use those. Okay, so if we start off and we say, okay, let's work out the probability of having a Z-score less than 1 standard deviation below the mean. So that's going to be on page 36 of the table books. So you're looking down here at 1 standard deviation. So we're saying what we're getting there is the probability that any Z-score selected at random will be to the left of 1 standard deviation. And so that is 0.8413. Okay, so, and then from that, we're going to subtract, well, we want the probability. So like what I'd be getting there with that 0.8, whatever I said, would be everything in green there, everything to the left of 1 standard deviation. But of course, we need to subtract away this little region here. Let me use a different, well, there we go. Let's clear enough now? We want to subtract away that part there, but we know we can't get the probability of a z-score being to the left of -2. So instead we get the probability of a z-score being to the right of +2, but we can't calculate that either. We're going to have to calculate the probability of having a z-score to the left of +2 and then subtract that away from 1. So we're going to get the probability of having a z-score to the left of +2 and subtract that away from 1. That's when we're going to page 37. Here we go, 0.9772. So I'm going to subtract that away from 1, and we're going to get 0.0228. So I'm going to subtract that away from my 0.8413, and I'm going to get a final answer, which is 0.8185. And after all that work, I might be tapping myself on the back saying, God, that was great, well done. But then I had to remember, I got to read the question. And the question said, calculate the percentage. So just to make sure you get full marks, you want to give the answer to the question that's asked. So the question that was asked was, find the percentage of cars expected to have a speed between 89 kilometers per hour and 98. And so the final answer is 81.5% of cars would have a speed between 89 and 98 kilometers per hour. Okay, so there you go. That's your first 10 marks. Now, we're on now to part B. A traffic analyst estimates that 20% of the cars travel too fast on this section of motorway. Calculate the slowest speed that would be considered too fast. So, it's considered by too fast by this traffic analyst. So, we don't know, we don't need to get into the whys and the maybes of whether this person is right or wrong, but we're just going to calculate it. Now, so we're basically, again, you're talking about a bell curve. You're talking about the fact that there's 20% up here, but we're not going to be able to calculate that 20% because we know the way page 30, 36 and 37 work, that we're going to be calculating to the left of a particular Z value. So instead of thinking about the 20%, we're going to be thinking about the 80%, which would be the green section. So 20% above corresponds to 80% below the speed limit, or this too fast. Now, you got to look on page 36 for 80%. I know students sometimes go wrong here. They go down here looking at that 0.8. But remember, that is the number of standard deviations to the right of the mean. We're looking over here in the body of the page, and then those are your probabilities. So we're looking for something that looks like 80%. So you're looking for 8, so some of you might be drawn to that one, but this number here is closer to 80%. It's 79.95%, and that corresponds with 0.84 standard deviations. So the 0.8 standard deviations nearly turned out to be right, but that was just random. So it's 0.84 standard deviations brings you to the correct, the correct Z-score and the correct probabilities associated with it. So 0.84 standard deviations means 20% is to the right of that Z-score. Okay, so now we have the Z-score in question. We know what mu is, we know what sigma is, so now we must calculate x, which is the speed. So we fill in everything, multiply across by 3, add 95, and hey presto, 97.5 kilometers per hour for 10 marks. Now, if you've seen enough of these questions, you will see that kind of idea comes up an awful lot, and there isn't that much work to do to get that 10 marks. Okay, so that's part B. Now we're on to part C. So, okay. Now, part C, there's a bit more of a context to this, so we'll have to look at this and read it. The speed limit on the section of road is 100 kilometers per hour. A speed camera has been installed. What are the percentage of cars that would be expected to be exceeding this speed limit? So our analyst had felt that 20% of cars were speeding. So, but when they worked that out, then it was 97.5 kilometers. Okay, that was the speed they were traveling at. But in this case here, we're talking about an actual speed limit of 100 kilometers. So what would we say? Well, in this case, x is actually going to be 100. That's the speed. So we do fill in our standardizing formula, put in the 100 for x. Mu is 95. Sigma is going to be 3. So it's, you can see it's 1 and 2/3, 1.6 recurring standard deviations above the mean. So like, you're up there somewhere. 1.67, because we're going to say, well, the probability of having a speed greater than 100 is the same as the probability of having a z-score greater than 1.67. And why do we say 1.67? Because the z-scores go to 2 decimal places. So like 1.67, and what's that going to give me? 0.9525. So 95.25% of the values will be below that. Of course, that's giving me the probability of having z-score to the left of 1.67 standard deviations. So there's my 0.9525. So 4.5% of cars are actually speeding. So 4.5% are traveling above 100 kilometers per hour. So 5 marks for that. If 15,340 cars pass the camera, how many cars would you be expected to be exceeding the speed limit? So this is like an expected value question. We have a number of cars, this amount of cars, and we have the probability that any car is speeding is 4.75%. So to get your expected value, you multiply the number by the probability, and you get 728.65. So to the nearest whole number, that's 729 cars would be expected to be speeding. So 5 marks for that. Tick one box to complete the following statement. The estimate made by the traffic analyst in part B was either realistic or unrealistic. Justify your selection using the answers from part B and or from part C. So in that case, right, you're saying like, well, was it realistic that 20% of cars would be speeding? Like, did they just have a kind of a misunderstanding or misjudgment really of what speeding was? And I suppose it was unrealistic because we found that with a speed limit of 100 kilometers per hour, we found that actually only 4.75% were speeding. So 20% to be going over a speed of 97.5. Well, it wasn't a kind of reasonable estimate of what it was to be speeding. So that's a question now that you could debate back and forth as to what the answer is, and different possibilities. And that's the nature of kind of stats and probability. It's not quite the same as algebra. And there's going to be another one here in a moment with a similar sort of idea that you could debate what the answer was. Which curve on the graph best represents the distribution of speeds of the car on this section of cars on this section of motorway? Tick the appropriate box to indicate your answer. So in this case, right, you're looking at, you have these 6 of them here, A, B, C, D, E, F, and you're saying, well, which is going to be the most likely to be representative of the actual speeds of cars? So we think back to our information that we have. So cars are traveling with an average speed of 95 kilometers per hour and a standard deviation of 3. So when we look at it there, okay, well, it has to be either C or D because that's where your average of 95. And in that case, then, okay, sigma is 3. So 3 lots of 3 would be 9. So that'd bring you over to 104. So in that case, then your answer is going to be C because it's going to bring you up here 3 standard deviations, bring you to 104. And 3 standard deviations below the mean would bring you to 86. So C is the answer there for 5 marks. Obviously very quick if you know what you're doing. Which of the graphs represents the distribution speeds for heavy goods vehicles, HGVs, on this section of motorway? Tick the appropriate box to give your answer. So in this case, right, there's a bit of imagination required here. You got to think about heavy goods vehicles. We can say it's clear that the average would have to be lower, the average speed. So how much lower? Well, in given the options here, I think it's fair to say that the average speed could be down to, say, I think we're looking at 87 here for our average speed. And our standard deviation, well, one could, say, well, it could be more, it could be less, right? But because I suppose there's a wider room to get up as far as the speed limit of 100, you could certainly make the case that the standard deviation could be larger. Equally, you could imagine some heavy goods vehicles going very slowly. Now, other people might suggest so that what we're kind of going on here is that the standard deviation or the average will be 87 and the standard deviation will be 5. However, you could make a case for other possibilities, and they were allowed for in the marking scheme as well. So you can check the marking scheme to see how many marks you get for your answer. But I think that's a nice question because it gets you to think about the speed and the standard deviation of these different types. From the graphs, identify any two distributions with the same mean. And again, right, as you're looking at this now, you don't even need to think about cars or heavy goods vehicles. You're saying, okay, what graphs have the same mean? Now, there are plenty of possibilities here because you could say, well, A, E, and F, any two out of those three have the same mean. Or you can say C or D. So either the ones in the green or the ones in orange are perfectly fine. Okay. And then identify any two with the same standard deviation. Well, in this case, the same standard deviation, the same sigma. B, D, and F both have this, those three all have the same standard deviation. Okay. So in that case, I think it's a standard deviation of 5, isn't it? And then the other C and E both have a standard deviation of 3. So either the ones in green or the ones in orange, any two from those would give the same standard deviation. So there's 5 marks for that last part. And again, some people would think that's such easy marks, and other people mightn't have even tried it. They'd say, God, I don't know what that's all about. So that is our first of our long questions. We're finished with question 7 of paper 2. We're now going on to question 8, something very different.